Iterate. Let's see. Seem to be streaming. Seem to be alright. Audio is fine. So yeah, today, I mean, like a few days ago, I played. I mean, like I dive decently deep into the CUDA programming thing, like programming stuff on the GPU, and following some course on it. And when I followed the course, I noticed that a lot of the parallel computing like patterns are very very similar to what functional programming proposes, but more oriented toward arrays. And I've heard of APL before, which is an array-oriented programming language, which seems really strange with all kinds of strange symbols, like so. Maybe I should zoom actually. With all kind of strange symbols as you see on the top. And yeah, it's a language, a small language, so I think that's all the characters that you can have in the programming, plus numbers and letters for like strings and so on. So yeah, it's a bit esoteric, but I don't think it's like it's not really a joke programming language. It's more, I would assume, what do you say? Not educational, but maybe a more academic programming language. And I know there is other variants that are a bit more modern than this, but I think APL is the OG array-oriented programming language. So yeah. But yeah, maybe to exemplify this, maybe I think there is in CUDA there is a reduce, for example. So you probably know reduce. I don't know. Do they have a visualization? So yeah, you have the regular reduce, which is like you have an array and you have like some value that is gonna get updated and you iterate over the array and you have some operation. For example, your start value could be 0 and your operator could be plus, and then it's gonna apply 0 plus every element of the array, and every time it's gonna store back the result into the value. And so in the end, you have the sum of the array, basically. But the thing is, you can translate those algorithms into parallel computing. And so, I don't know if they have a clearer view. Yes, that's it. So for example, here is your array, and if you did it like the serial way on the CPU, it would go like one element by one element and add them together. But on the GPU, you can actually have the sum of all of those by doing the operation on two neighboring cells, and then three neighboring cells, and then four, and so on. So you like you can do a lot more of those operations. You can do reduce faster, basically, in less steps and in parallel, which is nice. And it's also the case for like other common how do you say, patterns in functional programming, like filter, reduce, as I said. There is also scan. There is map, of course, the most obvious one. And there is, I think, plenty more of those. And so yeah, that got me thinking into, oh, I know that this weird programming language that is all about array programming and having those functions on arrays. And so I've been wanting to learn this for a while, and thought, why not? So yeah, so let's just read the introduction. Got a minute? Try APL. APL is an array-oriented programming language that will change the way you think about problems and data. With a powerful, concise syntax, it lets you develop shorter programs that enable you to think more about the problem you're trying to solve than how to express it to a computer. Try APL runs on Dialog, which is you can download for free. Okay, sure. Maybe I'll try that later. For now, I think just using the website is fine. Should I zoom out? Zoom even more? Yeah, no, that's fine. Or trade now by entering an expression. Use the language bar above to type the special APL symbols. Or clicking one of these expressions followed by enter, you see it in action. So if I type 2 plus 2, it will return 4 and so on and so on. And so an array is just a series of values separated by spaces. So that's an array. Oh, what happened? So 1, 2, 3 plus 4, 5, 6. Okay, and they added, they apply the addition on all of those. But apparently I cannot just like enter an array. Oh, I can. Okay, there was something strange, I guess. So I can just enter an array, and I'm guessing like a string is just an array of. Can I do? Okay. Oh, the strings are like with the single quotes. Yeah. Okay. Can I clear this by any chance? No. All right. Well, no clearing. So yeah, I can. So arrays are very simple. Generate the first 10 integers. So this little squiggly thing, they should really like give me the names as well. That would be nice. I guess in the learn section maybe they will give me the name. For example, if you do this, oh, not here, here, and then 10, 10, it will generate the number from 1 to 10. That makes sense. It's like a range in Python. Sum the first 100,000 integers. So yeah, you just generate the integers from 1 to 100,000. And then there is a plus, which is the operator you apply on them. And I'm guessing the slash is their version of reduce. So plus slash, yeah, clicking on stuff is gonna be annoying very fast, but okay. Yeah, that's pretty nice. And if I want to do like 1, 2, 3 plus the sum until 3, so it will be the same ones, but it works as well. Okay, d'accord. Okay, I understand. A long, slow way to write factorial of 10. Wonder why slow. But okay, yeah, it's the same concept. I wonder if x is like just x or if it's like a multiplication. Oh yeah, it's different. Okay. So, but slash, little squiggly thing, and then 10, and this is like factorial of 10. All right. Average is the sum divided by the count. So, and apply it. So I guess you can declare like a function with the brackets and the little left arrow. Oh, and I can just click it. God damn, finally. There is really no like clearing this. Clear. I use clear to remove all names from the thing. Clear. Oh. Yeah, that didn't work. And just help. Does it work? Primer, help plus, yeah. Can clear workspace. Clear. Can't you? Can I just maybe refresh it and yeah, okay, fine. Let's just refresh it. And so I can just click on it and it will do the average function. And so there is still this kind of plus, so I'm guessing that's some kind of sum, and like the little strange W, which is probably not a W, is the variable, which is here in the top right corner, and then you divide that. I'm guessing the triple unequal means the length, and so that's the average function. And so you can do then avg 1, 2, 3. Oh, my bad. I need to do this first, then enter. Then enter, then avg 1, 2, 3, and then it's 2. Okay, that makes sense. Can I just I can just also remove it like so. That makes sense. All right. Okay. Then throws, store 10,000 dice rows, question mark, and then this, and then P6. I'm guessing P6 is yeah, P6 is from 1 to 6. Okay. Then 1, so +/1 equal throws of how many ones? Okay. Okay, so it's like 1 equal, so it will be, it's like a mask in pandas or something like that. It will be like 0 where it's not equal to 1 and 1 where it's equal to 1, and then you do the sum of those and then it's a count. Okay, frequency of all 6 possibilities equal throws. Okay, that's too complicated. You can do strings stuff as well, which is cool. And yeah, okay. What can APL do for you? Are you a problem solver, matter, or a programmer? Problem solver will benefit from APL's ability to concisely express advanced concepts without getting bogged down with a lot of the computer-easy syntax. Programmers benefit from APL's productivity and brevity. Shorter programs mean quicker development time and less code to maintain and debug. Okay, yeah. I mean, probably will never get used in real life, but still fun to think about. Not save between pages unless you opt in. Okay. Learn. Let's learn stuff. We use the Jupyter Notebook format to provide interactive lessons. Limitations apply. Limitations apply. So primer is like a cheat sheet, and learn is learning. Okay. Okay, but I'm just curious, is there an easy way to clear the stuff? Erase. Not really, no. I mean, that's okay. That's okay. No. For full functionality, download Dialog APL. Dialog APL, okay. Jupyter Notebook URL, okay. Using the try APL tutorial, press enter or click on the next button to progress through a notebook, okay? These tutorials are Jupyter notebooks using Dialog APL kernel. They can be downloaded on this website. First, we'll cover how to use the interface. Yes. Yeah, I can go back. Awesome. Restart. Yeah, that makes sense. Return to learn. Yeah. Can be modified and re-executed. APL code block. That code will be copied into the session pane. Okay. Single line expression can be modified and re-executed in try APL. Single line expression can be modified and executed. Okay. Clicking on the purple code will place it there. The session is like a text editor. You can go up and edit any text in the right hand pane. Then press enter to execute that code. Like, sure. Cycle through. Control Shift Backspace. Okay, that's cool. Cycle forward. Okay. Feature and limitation. Yeah, okay. Can we skip to the part where I'm actually learning the language? Okay, okay. Okay. No, it's awesome, really, but come on. Okay, good. APL expressions. APL is a mathematical notation which just happens to be machine executable, i.e. be a programming language. APL expressions consist of functions, array, and assignments. They may also have trailing commands beginning with the lamp symbol. This is really called the lamp. I would call it an Among Us character, but oh well. Beginning with the lamp, the Among Us symbol, a glowing bulb filament will light new. Okay, so this is a comment. Very strange way to start a comment, but oh well, very strange programming language. You can have multiple expressions on a single line by separating them with diamonds. Oh, okay. Again, very strange way of separating expressions, but weird programming language. Okay. Functions. We call all code that can be applied to data functions, even primitive built-in things. So plus f and f in f of x are both functions. APL operators are something else. Okay, makes sense. Plus as a function, nothing too fancy. Minus as a function. Many APL functions can be applied as prefix, monadically, or infix, dyadically. Usually the monadic and dyadic form are closely related. So minus b is 0 minus b, okay. -3. APL uses high minus to indicate negative numbers. Oh, okay. That's very strange again, but oh well. And so the high minus is there, okay. Arrays. All data resides in arrays. An array is a rectangular collection of numbers, characters, and arrays. So you can have multiple dimensions of array, that makes sense. Arranged along 0 or more axes. We can use more specific terms for some arrays, like a single number is a scalar, a list is a vector, and 2D arrays are matrices. Vectors can be formed by just placing elements next to each other. Okay? Yeah, that's a vector, makes sense. Strings, as APL has no string data type, we just use character vectors. Lists instead, characters and characters vector are in single quotes. That's a character, and if you put multiple characters, it's a character vector. Okay. Numbers. A number is a number. A number is a number. You don't have to deal with internal representation, as APL will internally convert between bit Boolean integers of various sizes, floats, base 10, decimal floats, and complex numbers, all seamless to you. Okay, that's nice. Must have some overhead to it, but I mean, it's like, yeah, as I said, more academic programming language, so it makes sense that they abstract these stuff away. Okay. Yeah. And so I'm guessing the Boolean expression here becomes a 1, and so it's 3. Makes sense. No, can I go there? Yeah. Okay, it converted from integers to float. Then here it will convert the 1 to a float as well. APL takes care of binary versus decimal inexactness too. So 1 times 1 divided by 3 is literally 1. Damn, that's pretty cool. That's pretty cool. Negative numbers are indicated with a high minus. Yeah. Very large or small numbers use exponential notation. Yeah, that makes sense. And we can generate them ourselves this way by -6 or 6. And if I just do 1e and just 6 instead, we get what we expect. Complex numbers are similar in that they use j to separate the real and imaginary part. Yeah, that makes sense. Sure. Assignments. You can assign a function or an array using the left arrow. Yeah, that makes sense. This avoids all confusion of assignment with equality. Is just another comparison function. Yeah, so like 3 equals 4 is just a comparison and not an assignment. Yeah. 2 equals 2, sure, whatever. Why use APL instead of a conventional mathematical notation? Mathematics has some inconsistent and weird notations like negation and factorial being on opposite sides of their argument. Exponentiation doesn't have a symbol. Rather, the exponent is raised and made smaller, and magnitude has 2 symbols, a vertical bar on each side. APL harmonizes everything to be inline, pre-infix, single symbol, so factorial is exclamation point b, raising to a power is a times b, okay, little star b, and magnitude, absolute value, is pipe b. Okay, yeah, that makes sense. Okay. That's very confusing that this is exponentiation and not multiplication. I mean, for a programmer, I guess for a mathematician, maybe it would be slightly less weird. Traditional mathematics also has a complicated and ill-defined order of evaluation. For example, is sign or multiplication evaluated first in sine alpha with phi? How about sine alpha cos beta? And while functions that supposedly are on the same level evaluate from left to right, this doesn't apply to exponentiation. And how about a divided by bx? APL has just one simple rule: all functions take everything on their right as right, or only arguments. Okay, that makes sense. I guess it's like the kind of like the Lisp or Haskell way of doing things. Like you start with the function name, then all its arguments follow, and I'm guessing separated by spaces or no space. And if you want to change priority, you just put parentheses around the expression. Easy enough. 1 plus 2 times 3, okay. Oh. But then they have stuff like this. Oh, okay. So they don't give a shit about precedence. They just okay. So APL has just one simple rule: all functions take everything on their right as right or only argument. Okay, but how about infix notation? Well, it's in between. So I would have to do parentheses 2 times 3, then plus 1 to get the 7. Okay. Okay, that's not 100% clear to me, but I mean, I understand that they don't care about mathematical precedence, so just have to keep that in mind. You may, of course, use parentheses to force the order of evaluation, which I just did. These rules apply to all functions, whether built-in or user-defined. Know the syntax of one and you know the syntax of all of them. Okay, that's good. That's it? Ah, yeah, that's it. All right. Arrays. Arrays. Can I delete all of this? Oh, can I just... All right. Throughout this lesson, there are snippets of code as examples. You are encouraged to edit and experiment with these. It will greatly improve your understanding. All data in APL resides in arrays. An array is a rectangular collection of numbers, characters, and arrays, arranged along 0 or more axes. Numbers and characters are zero-dimensional arrays and are referred to as scalars. Characters are in single quotes. Creating a one-dimensional array is very simple. Just write the elements next to each other, separated by spaces. This syntax works for any data that you want in an array: numbers, characters, other arrays, etc. A string is just a character of vectors, which may be written into single quotes around the entire string. Parentheses are just a group of... parentheses are used to group array of items. Yeah? So yeah, this is a vector or an array. APL is just a character vector or string. Yeah, same thing. And here I'm guessing is a two-dimensional array. Numbers are very straightforward. A number is just a number. It doesn't matter if it is an integer or not, nor if it's real or complex. Negative numbers are denoted with the high minus. You can also scientifically use scientific notation with E or uppercase E. So a million is 1E6. The items of an array can be of different types. Oh, okay. I wonder how that's optimized though, because that looks really slow. I mean, it seems like it would be very slow. I guess maybe it does some check, like if all the elements of the array are numbers, then like optimized by just not having pointers to them. Or maybe they have like kind of like prefixed pointers where they have a flag in the pointer to know if it's just a small integer or a pointer. I think that's how maybe Lisp, some implementation of Lisp do it. What did I do? I clicked on the wrong thing. So can be of different types. Yeah, that makes sense. Yeah. The items of an array has a rank and a depth. The depth is the level of nesting. For example, sexy looking UI indeed. Yeah, I don't know about sexy, but yeah. If you look at the top bar, you know that's a good programming language, am I right? But yeah, it's just basically a Jupyter notebook with some other interpreter, you know, for a strange programming language. The depth of is the level of nesting. For example, an array of simple, i.e. non-nested scalar has depth 1. An array containing only depth 1 arrays has depth 2. And a simple scalar, a number or a character, has depth 0. Yeah, that makes sense. That's just the number of dimensions. However, for some arrays, it's not so easy. An array may contain both vectors and scalars. I guess in this example, we have a vector, a scalar, and then another vector. Yeah. Oh, it's strange, they put B without the quotes and it still worked. Oh well. However, for some arrays, it's not so easy. In case like this, the depth is reported as negative. Okay, sure. You can find the depth of an array with the function triple equal. Okay. No. So that's 0. That's a vector, so dimension 1. And that's 3. Yeah, makes sense. And then this is -2. Okay, sure. Because there is scalars and vector to the thing. Rank. The concept of rank is very important in APL and it isn't present in many other languages. It refers to the number of dimensions in the array. So far, we've only seen rank 0 arrays, scalars, and rank 1 arrays, vectors. You can, however, have arrays of other ranks. A rank 2 array, for example, is often called a matrix or a table. Arrays are always rectangular. Each row of a matrix must have the same number of columns. Each layer of a 3D block must have the same number of rows and columns. As our screens are only 2-dimensional, higher rank arrays are printed layer by layer. Creating arrays of rank greater than 1 is only slightly harder than creating vector. To do so, you can use the function row. Okay, I have to remind me that this is row. So this guy, it takes a vector of dimension length. Okay, so it's a vector of the dimensions as an argument, as a left argument, and any array as a right argument. It returns a new array with a specified dimension filled with the data of the right argument. Okay, I get it. It's like the reshape in NumPy or whatever. So if I do like a little squiggly thing, let's say 6. No, it's not that. Little squiggly thing 6. Yeah. And then if I do, what is it? So it takes a dimension on the left. Yeah, so we do row, which is this guy, and then here it takes a vector of, I say, 2, 3. Yeah, okay, and then it shapes it as a matrix of 2 by 3, which makes sense. Okay, yeah, that's pretty concise. It would be the NumPy equivalent of like NP array, like range 1, 7, and then reshape like 2, 3, I think. Yeah, not too bad. Can I execute Python? No. To do so, we can use the function row. Yes. It returns a new array with the specified dimensions filled with the data. Are you streaming daily now? Yeah, apparently. I just was like, why not? I'm not really planning anything, just randomly streaming when I feel like it. Same thing for the videos. This YouTube channel is just a hobby. So who knows? Maybe I will stream daily. Maybe I will take a 1-year-long break. Nobody knows. Filled with the data of the right argument. If there is too much data, the tail just doesn't get used. If there is too little, it gets recycled from the beginning. Okay. So 2, 2, and this will create a 2 by 2 matrix. This, okay, I already did my test, I understand. Or you can do that with letters. Okay, but like if there isn't enough data, it will just repeat it. That makes sense. And if there is too much data, it will just trim it, which also makes sense. Okay, no, I want to go there. It doesn't matter what the rank of the right argument of P is. Matrices don't have to contain only scalars like vectors, and all other arrays, they can be nested. Yeah, that makes sense. That makes sense. Okay. So here the elements of the matrix are just vectors, and we reshape those. So we have some kind of a tensor action going on, like multi-dimensional, like matrix that are more than 2 dimensionals. Oh, I'm breaking everything. Just leave me alone. Yeah, yeah. Okay, it's doing stuff. That's a bit more tricky, but basically it's generating a matrix of x's and other matrices of zeros and ones, and then it's nesting them in another matrix. That makes sense. Depth is general to arrays of any rank. The depth of an array isn't just the nesting level of vectors, as shown previously, but of any array. So an array of depth -1 matrices has a depth 2, and a matrix of numerical... Okay, this is getting strange and technical. Let me just see the example. Just learn that APL stands for a programming language. Yep. That's, you know, I mean, it's a programming language, so what can you do? Like, just name it a programming language. I think it's pretty old as well. So the APL programming language. Let's see. Wasn't it created like in the 70s or something? In the 60s. Like, named after a book, A Programming Language is just is a program developed in the 1960s by this guy. So yeah, pretty old. Oh, and they have keyboards like this. Damn, that's a flex, huh? And they put that on like mainframes and shit. That's pretty cool. That's pretty cool. Alright, anyway, most accurate name. Yeah, I mean, every programming language should be named a programming language. And you just number them. You say programming language number 1, 2, and 3, and so on. Depth is general to arrays of any rank. The depth of an array isn't just the nesting level of vectors as shown previously, but of any array. So an array of depth -1 matrix is depth 2 and a matrix. Okay, I'm so confused. So here we have a matrix. So I can copy paste this, and we have a matrix of 5 by 3. And so if we check the depth of this with the triple equal operator, it's 1. Which doesn't make much sense to me. So, okay. I'm guessing rank is like the virtual dimensions and depth is actual dimensions. So what I mean is that this in memory is represented as just an array with a shape. But like in memory, it's still like one-dimensional. But if you do like vectors of vectors, then it's actually in memory multiple arrays with an array of pointers to them. At least that's my understanding. Okay, so it's doing stuff. Yeah, of course, all arrays of uneven depth are dealt with in the same way as vectors. Yeah, I'm getting a bit confused with the depth thing. But but okay. A depth of the previous example is -3 because A in APL is a depth of 3. Alright, whatever. APL also has empty arrays, so it's like 0 with a squiggly line crossing it, so this. Okay, I'm so confused. Okay, I'm executing those. The function row also has meaning monadically. When applied to only one argument, it returns the shape of its argument, the length of its dimensions. Okay. Okay, I see. Okay. 0, that makes sense. That makes sense. There is distinction between a single row matrices and vector, even if they look the same when printed. Okay. Okay. Node identity uppercase X. What is big X? Is it like a symbol or is it just uppercase X? It looks like just uppercase X. The identity X is equal to the depth of row X, row A. After reshaping an array with X, its shape will always be X. Okay, this is heavy. The length of the shape of an array is equal to its rank. The length of a shape of an array is equal to its rank. Yeah, that makes sense. Therefore, we can find the rank of an array with row, the shape of the shape. Yeah, it's fine. Since a scalar is rank 0, the shape of a scalar has length 0 and it's an empty vector. Yes. Okay. This is dimension like rank 1, this is rank 4, this is rank 0, and this is something. Rank null, I guess. Oh no, it's not the rank, it's the dimension in this case. You can use row to convert between a rank 0. You can use row to convert between rank 0 scalar and rank 1 vector. Okay. Okay, finally the end. Okay, but my understanding is that row is used to reshape an array or get its dimension, and the distinction between rank and dimensions is, I want to say linked to memory, but apparently not really. So I don't really understand the distinction between those two, but I'm not sure it will be hugely important. I mean, apparently they say it's a key concept, or they say it's like different from other programming languages. But yeah, I don't know if how useful it will be. Anyway, that was heavy. So there is functions then. Functions. Maybe I should just clear this. A function can be applied to data in two ways, dyadically or monadically. That is, a function that can be applied to either one or two arguments. Most primitive functions have both a dyadic and monadic function definition. For example, minus when applied dyadically is subtract, and when applied monadically is negate. The enter doesn't work anymore. Dyadic, monadic, yeah, okay. We distinguish between two types of function when it comes to applying to data. Scalar functions are mixed functions. A scalar function will penetrate the array that it is applied to all the way down to the simple scalars. Okay, so no matter the dimensions, it will, like if you apply +2 on a vector or a matrix, I'm guessing it will just do +2 on every single element. Example of scalar functions are the arithmetic function, plus minus times and divided. A worthy note is that APL uses traditional mathematics notation for multiplication and division, and the star is used for exponentiation. Okay. And so you can just have a vector and apply negation on it to negate every single element. That makes sense. And if you negate on a thing that has a lot of dimensions, it will just negate every single element one by one. See that the structure of the array remains the same, only the content is changed. The same is of course true for high ranks array. If you're unfamiliar with the concept of rank, you can check out the notebook on arrays. Okay. So same thing where they generate a multi-dimensional or multi-rank whatever array, and they applied negate on it and it just goes over every single element. When a scalar function is applied dyadically, the scalars are paired up between the two arrays and the function is applied between the pairs. If the shapes of the arguments do not match up, an error is reported. Yeah, that makes sense. So I'm guessing like 1 to whatever plus something like this, that works. But if I do 1, 2 plus like something that is larger, that will be an error. Yeah. Yeah, and he will show me the same thing I just did. And this applies as well on more than one dimension or more than one rank. Yeah, that makes sense. They just do element by element. They can also do it on matrices. The shapes of the arguments need not match up exactly. If one of the arguments is a scalar, you get what is called scalar extension. The scalar is distributed across all the scalars of the other argument. Yeah, that makes sense as well. So if you do 2 plus 1, 2, 3, it will apply +2 to all the elements of the vector. Yeah. No problem. Yeah, and it does this for more than one dimension as well. Mon Dieu. Additionally, scalars inside the arrays can be extended after the items have been paired up. What does this mean? Scalars inside the arrays can be extended after the items have been paired up. All of the arithmetic functions also have a monadic definition. Yeah, I didn't understand this, but I guess it did like the vector 1, 2, 3 plus every single other vectors that were in the matrices. Maybe. Yeah, that looks like it. Huh? That looks like it. All of the arithmetic functions also have a monadic definition. Minus is negate. Divided is reciprocal, so 1 divided by the element. So if I do, but that's, yeah, I guess that works. No, please, like divided 2, that's 0.5, yeah, makes sense. Plus is complex conjugate, acts as an identity for real numbers. I think I almost forgot what a conjugate is. Identity for real numbers. Isn't it the length of a... No. Yeah, no, I forgot. I know it has a nice geometrical interpretation once you put it in 2 dimensions, but yeah, whatever, I forgot. Times returns a unit complex number in the direction of its argument. Signum on real returns a unit complex number in the direction of its argument. Okay, so it's like normalizing a vector, but for complex numbers, and signum for real numbers, so 1 or -1. So if I do this, some number, it's 1. If I do this, then high minus, and some other big number, it's -1. Oh, and if it's a 0, I guess it stays 0. Okay. Raises e to the power of its argument. Ooh, that's funny. Oh, my bad. Okay, have a go at testing them out by modifying the following. Yeah, I just did, it's okay. Mixed functions. Mixed functions apply to larger structures of the argument. For example, the row of a matrix, or just takes entire argument. They can treat each other differently in this respect. Mixed functions apply to larger structures. Oh, okay, so it's like row by row or column by column, stuff like this. Monadic row shape is a mixed function. It returns the shape of its argument, the length of its dimension. Obviously, this wouldn't be very useful as a scalar function. Row takes its entire argument into consideration. Yeah. Yeah. Okay. There are many functions in APL and I really need to put like an anti-cough thing on my mic. If that exists. There are many functions in APL and they won't all be contained in this notebook. The row has been covered in more depth in the array notebooks along with monadic triple equal, which is... Yeah, I thought triple equal was the dimension actually. But row also gives the dimension. I'm a bit confused though. What is the triple equal again? So triple equal 1, 2, 3. No, just 1 triple equal, please. That's 1. And then row, which is this, 1, 2, 3, is 3. So row in this case is the length. Yeah, okay. It's not really the length though. Yeah, I'm still confused about the concept, the difference between depth and rank. But oh well. There are many things, they won't be covered, yes. Can I... To define your own functions, you have 3 options, dfns, tradfns, or tacit function. A user-defined function behaves the same way as a primitive. As a primitive function, it takes maximum of 2 arguments, left and right, and it is called either prefix monadically or infix dyadically. DFNs. DFN, dynamic function, is an APL expression enclosed into braces where the left and right argument are referred to by alpha and... I forgot what this means, how you call this. Because I don't want to call this W for the rest of my life. How is this called? Try again. Yep. Really? Can't I like search stuff? Oh, it's just literally an APL. Omega, okay. Let's call it omega, I guess. For monadic function, only W is used. Okay, so alpha and omega are the left and right, and for monadic function, it's only the right one. Yeah, makes sense. Yeah, times, and then you do times like so. Dynamic functions are an anonymous function, they don't require a name. This means that they can be used inline like a primitive function. Yeah, okay, that makes sense. That makes sense still. So this generates a matrix of dimension alpha 1 from omega, and omega is APL is fun, and the alpha is 3. That makes sense. Is APL used today with those weird characters? I think it's used for stuff like little puzzles or just fun and education. I've seen content on it on YouTube, for example, so yeah, it's still used. I think it's a very niche thing, but there is a community around it. It's not like you're completely alone. I think there is this guy like how is it called? Code Reporter. Yeah, I have him here. I think he does a lot of videos on APL. Yeah, see APL stuff, and then there is all the newer versions of APL like BQN and stuff like this. And so, for example, I think he compares somewhere like he takes a little puzzle and compares the solution in APL, in C++, in Haskell, and stuff like this. So, for example, yeah, maybe you can
Welcome to
like watch this. He just solves like a advent of code in APL, and yeah, it's pretty cool. Like he has a better editor than me, but yeah, he just solves the thing in APL. So yeah. Dynamic functions are anonymous functions. They can be, yeah, okay, understood that. The dynamic functions can be nested as much as you like. Alpha and omega will always reference the argument of the dynamic function defined by the immediately enclosing braces. Makes sense as well. Okay, so there they have like a dynamic function inside of a dynamic function. Okay, I fucked their example up a little, but it's okay. Inside a dynamic function, you can perform an if A then B else C check. It takes the form. Oh, that's quite strange. It takes the form A2 dot B diamond C. I must evaluate to a Boolean singleton, which just means that it is 1 or 0 whose shape consists of only ones. So, okay, I see. There are many functions inside APL, so if I put this to 0, I get false, but what if I put this to some, I cannot do this, it's only 1 or 0, okay. And what if I do this with like a vector of ones? No, okay. I guess I would have to reduce it. There are many functions in APL that return the Boolean. So, but could I do like 1 equal slash this? No? Isn't there like a 1 equal slash? I thought the slash was reduce. Anyway. There are many functions in APL that return booleans. For examples are comparison. Oh, the comparisons are the same as regular programming. Awesome. I mean, almost the same. And they are... Where are they? They are here. The comparison are all scalar functions. Okay, yeah, that makes sense. That makes sense. Oh, okay. To perform recursion, you can either use the name of the function or the symbol, the opposite of delta, which refers to the function it's in. If it's not named, you... So could I do like a shitty factorial function? Just for training. Can I do tick, 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 tick? So to take only one number, so that's omega. So it would be... you need to do omega is equal to 1. Then we do... If it's equal to 1, it will be 1. Where's the 2 dots? Is 2 dots just 2 dots on my keyboard? I guess so. If it's 1, it's just 1. Otherwise, then I have to do the little diamond. Wow, you little diamond. Come on, show yourself. God damn, that's a pain. Diamond, there. Okay, otherwise, it will be W times... and so the reverse delta symbol of W minus 1. Is that the thing? Oh, fuck yeah, I put W. What a stupid... what a stupid man that I am. So this is not W, this is omega. And this is omega. Okay. Ooh, and if I do 10... no, it's exclamation point 10. Okay, it works. So I can do like my first function in APL. That makes me so proud. Okay, but that's quite nice actually. Like referring to the current function with some symbol. That's just a very concise way of doing recursion. I like it. I like it. Maybe I should save some example. Claps. Yeah. Let's try to do the Fibonacci. Maybe. I will also just keep my APL example. It's in some files. Just so that I can like look at them maybe later. Let's do the Fibonacci thing. So Fibonacci would be... It would take just how many elements do we need? And it would take only one argument. Yeah, so again we do the... Actually we can, since they said dynamic functions are like this, we can... And so let's say we want the third element of the Fibonacci sequence. And again it will be if W is equal to 0, then we return 0. That's gonna be tricky. Can I put the... Where is the little diamond? I lost the diamond again. Okay, it's there. Otherwise, let's put parentheses, otherwise I'm confused. If W is equal to 1, then it's 1. Else we do so confused. What was it again? It was like this. Again, let's put parentheses because otherwise the precedent stuff, I don't get it anyway. So it's the current function with not W. Why do I keep putting W? It's omega. Omega, and it's omega minus 1 plus the same function. I mean, it's very unoptimized Fibonacci sequence, but we do again omega minus 2. Syntax error, unpaired parentheses. So we have these parentheses, we have these parentheses. They look paired. Well, why do they say it's not paired? Not sure. Can I just remove the parentheses? The third element of the Fibonacci sequence, so the Fibonacci sequence is like this, then 2. Let me just write it down, then 5, then 8, then 12, then 20. I think that's it. And so if I do this, and I do, let's say 1, 0, 1, 2, 3, 4, 5, 6. Let's say the sixth element. Fuck, okay, never mind. Oh yeah, right. I have to do this plus this. No, but that works. Why doesn't that work? More parentheses? Okay, so I'm guessing the plus took precedence over the other. But yeah, in this case it's good, so I can do my little fib is equal to this, execute that, and then I can do fib, I want the sixth element, and then I can do fib, 10th element, and I can do like 13, and so on and so on. Okay, that's nice, I will save that as well. I hope there is a better way of doing a conditional, like so, because that was quite annoying, like if 0, it's 0, if 1, it's 1, and then it's like a lot of if-else. But yeah. But yeah. Great. Yeah, that's pretty neat. I really like the recursion with just a little symbol like this. Kind of cool. The conditionals, not so much, but maybe there is a better way. To perform recursion, you can use this symbol, refers to the function it's in. If it's not named, you have to use the downward delta, which is generally recommended so that you may rename a function without having to change its definition. So that you may rename the function without... Okay, sure. No, I want this. Okay, well, they do the factorial example just right after me, so oh well, I guess I'm very not original at all. And their example is better. I mean, it's slightly shorter, I think. Maybe not. Yeah, I guess it doesn't really matter. They just reverse the condition, and then they show that you can use the downward delta symbol instead of fac. Okay. Okay. A tacit function is an APL statement that does not have data on the right. The simplest tacit function is a single function. Yeah, so, for example, if I do just plus, that's a function, that's the function plus. Okay, so Like the functions can be treated as values, basically. No, give me that. So yeah, I can assign plus to a function if I want to. Longer tacit functions are often referred to as trains, where each car is either a function or an array. We'll start by going over monadic trains. A two-train FG is called an A-top, which is equivalent to f of... So fg of x is equivalent to f of g of x. F is evaluated atop the result of g. Okay, so you can, what's it called again? Do currying, function currying, just like in a Haskell. By just omitting the argument of a function, you get back a function. So for example, if I want to do like f is a function is just 2 plus. Oh, I cannot do that. Can I do f is plus 2? Cannot do that either. Is it because invalid modifier assignment? Okay, is it because of the letter? G is doing parentheses. Plus 2. Ooh, okay. And so I can do just g of 5. Oh, yeah. That just gave me the number plus 2. Alright, never mind. Maybe I don't understand it this well then. There doesn't seem to be currying. Since a tacit expression does not have data on the right, to use an unnamed train, it must be placed inside parentheses. Okay, so times minus. So that will do, I'm not looking at the result yet, but it will do like -1, but times what? Oh yeah, right, the times on a regular number is like the sign of it. So this will give -1, and then it will get the like it will reduce it to -1, 0, or 1. So this will become -1, this will become 0, and this will become 1. Alright, I get it. It's like function application. And this will... Oh, I have no clue. Yeah, so 1 is the reciprocal, it's divided, and the exponent is... I have no idea. I have no idea. What is the exponent of just a number? Oh yeah, it's e to the power of 3, okay. Okay. So e to the power of 0 makes 1, 1 divided by 1 makes 1, and so on and so on. Okay. Know that there are two types of tree trains, forks, which are closely related. The FGH fork and the AGH fork. Here f is a function while a is an array. Okay, this was a clusterfuck of a sentence. So FGHX is equivalent to FXGHX. Oh, okay. So G is treated as infix notation, and FH is a prefix notation. So it's gonna do like f of x, h of x, and then it's gonna do the result. Both of the results are gonna be applied to G, which makes sense. But also a clusterfuck to read, but okay. And AGHX is AGH of x. Okay, and so you can replace the function by a value, and it will just use that value instead of the result of the function. Okay, kind of. I mean, I understand it now. Will I be able to use it? That's something else. Can you? So they have row, plus, and triple equal. Yeah, but he's giving like pretty funky examples as well. So you just have a matrix, the shape plus the depth. Oh, okay, no, that makes sense. Never mind. That's easy. So depth is triple equal and row is the shape. And we just add two of those. Okay. This one seems a bit easier to understand. I will try to understand it. So yeah, but 1 here is just a number, so it will do 1 minus, I forgot what, x of 2. What does this do? Ah, this is just like the signal. Yeah, okay. So this will give 1 minus 1, so 0. This will give 1, then 0, then 2. Yes, okay. I don't know APL. Yeah, well, me neither. That's why I'm learning it. And yeah, it's a clusterfuck of a language, but I don't know. It's so concise. Like it looks so concise and weird that my interest got piqued. Yeah, for example, this is like how you do the factorial function. Kinda neat, no? Kinda neat. And how you start a comment is you have an Among Us character, so that's a plus. Dyadic trains have almost identical definitions to monadic ones. X, F, G, Y, F, X, G, Y. Okay, the sign of the difference. Yeah, that makes sense. Wow, yeah, that hurts. That hurts a tiny bit. The product minus the sum. Yeah, okay, that's fine. So they do 4 times 3 minus 4 plus 3. Okay. Which is 5 apparently. Dum, 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 dum. And so that's like in fixed notation, so dyadic. And this is also in fixed notation. It's just that it's a dyadic instead of monadic. Okay. Then they have this kind of stuff where okay, yeah, that makes sense. They are just like generalizing it. Inside trains, it's useful to have the function whatever and whatever. They should really give me the names, for fuck's sake. I'm gonna call it left stop and right stop. So left stop returns the right argument and the right stop returns the left. When used monadically, they both return the right. Okay. Yeah, no, okay, so 20 is just used 2 times. And yeah, here it should be just the same as just using row, so that shouldn't change anything. As far as I understand. For any train longer than 3, the rules are still simple. If there are more than 3 functions, the last 3 become a 3 train and are treated as a single function. Then it's either a top, a fork, or you have to repeat the previous step. For example, PQRS x becomes PQRS of x, which becomes PQRS of x, which finally evaluates to PQ of x or S of x. That makes sense. And so if I have more functions, they are just applied monadically, so prefix. If in the same way x p q r s t, y is equivalent to p x y q x r s x t. Okay, that does not make sense. That is not what I expected. For the rules are still simple. If there are more than 3 functions, the last 3 become a tree train and are treated as a single function. Then it's either a top, a fork, or you have to repeat the previous step. So like if it's even, it uses prefix. If it's odd, it uses infix. From what I understand, but this is funky. So this is like 4 row 1 plus times. Good luck, bye. Yeah. Yeah, good luck to me, fuck's sake. Okay, this is too much of a clusterfuck. A particular common use for trains is when you have a handful of conditions and you want to check whether the input satisfies all of them. This can be easily done using the scalar function upper caret. Logical AND, the conditions can be written as condition 1, caret, and so on and so on. Using trains takes a lot of the strain off the reader because the pattern is obvious. All the conditions are being checked on the input and then are ANDed together. Compare this to doing a bunch of conditions like so, where the input has to be explicitly referenced in each condition and the line is cluttered by parentheses. Yeah. Oh, there is no more examples. But so can I try to use a train for that? Like this, then this, and 2 equal? No, that doesn't make sense. Can I say has to be equal to 1 and equal to 1? That's syntax error. Condition 2, condition. Can I do this? Okay, that's a bit stupid, but okay. And that doesn't make sense. Oh, it does. Yeah, okay. Okay, so I finished the basics. That was the basics. God damn it. God damn it. So there is what I expect, like reduce and scan, arithmetic function, which we already went over almost. We can sort and grade. We can modify the rank and the depth, and we can generate random numbers. There is a Boolean algebra and comparisons. This seems to be a bit short, like there's a ton of other symbols there that are not explained here. Mathematics, logic and comparison, structural, Selection and set operation, search and ordering, operators, miscellaneous. Alright. Well, I'm gonna take a break. Fuck. But anyway, let's do arithmetics next. Oh. Yup. So, arithmetic functions. The arithmetic functions are all scalar functions. They... Can you hear the... I put the fan on. Alright, no. Cannot hear the fan. That's nice. The arithmetic functions are all scalar functions. They penetrate into nested arrays all the way down to the scalars. Welcome back. Thank you. Thank you. The standard functions plus minus times divided all act as you might expect. I'm just gonna click this. Yes, that makes sense. Yeah, still makes sense. Yep, okay. All of those functions can also be applied monadically. For example, minus x is negative x, or 0 minus x, divided is the reciprocal. Okay. We already saw most of these things. Monadic plus and times are designed for complex numbers, plus gives the complex conjugate, times gives a complex number with okay, they are just explaining that this is like for complex numbers as well, that's fine. As a power function, yes, we already know that. Yes, yes, yes. Square root. What? Oh, okay, you just do exponent of a, yeah, how do you call it? A real number, or like a number between 0 and 1, and you get a square root. Makes sense. A reciprocal. Yeah, that makes sense as well, I think. Monadically, actually, does that make sense? A reciprocal. Exponent minus 1. Yeah, I forgot about minus exponents. What do they mean? I remember that the fractional exponents are like a square root kind of stuff. But minus exponents. Yeah. My math is rusty. Monadically, time exponent x is e to the power of x. That's fine. Yeah. Oh. Oh, that's it. Arithmetic functions. Okay. Grading and sorting. Okay, this should be more interesting. There is no sort primitive in APL, although sorting can be easily achieved with the grade up or grade down symbol. Grade up takes... Oh, what the fuck is happening? Grade up takes an array and returns the indices of the major cells in ascending order. Okay, this sounds like just a very fancy way of saying just sort them in ascending order. Yeah, I don't know what the fuck that is. Where is it? There. Can I do like random numbers? Or I can't, I guess. Can I? Are you alive? He doesn't seem alive. He does not seem alive. Did I lose internet? Or is the website just dying? The website seems to be dead. Is my computer dying? No, computer is fine. Stream dead? Doesn't seem dead. Why you not working? Ah. Gotta go. Ah yeah, see you. Oh, okay. It's back, I guess. Maybe my internet cut. Grading and sorting. So what I want is just to try this and then yeah, can you 1 0 something like this, and okay, this is not what I expected. Okay, it returns the order of them. No? No, it doesn't look like it either. Okay, never mind. This might be more complex. So the grade up takes an array and returns the indices of the major cells in ascending order. It's easiest to understand with an example. So we have vector, then we do like so. This means that the smallest element is the second one. Yeah, in his case it makes sense. In my case it does not. Because my smallest element is 1, but he says it's the fifth one. But also in his case it doesn't make sense. Okay, this one makes sense because it's the largest one, but then what the fuck is this? This is 4. This means that the smallest element is the second one. Then the fourth also 1. Then the first 3. Oh, it's like the index. So it will be 1, then 1, then index 1 is 3, then it will be index 3 is 4, and then 5. Okay, this is what the fuck? Okay, yeah, I get it. Alright, so in my case, the lowest element is the fourth one, which is 1, and then the first one, which is 2, and then the second one, which is 3, and then the fifth one. And that's incorrect because, but maybe there was a bug, I don't know. Yeah, okay, there was a bug apparently. No, what? Why do you say 20 is before 51? That doesn't make sense. We can also use this to sort an array. Yeah, okay. What the fuck? Ah, so I guess you can index a vector like so. So if I do v1, I get the first element. But if I do v and 1, 2, I get 2 elements of it. Okay, and then I do v with this, and I sort the array. And so in my example, can I do like v2? I don't know. Is 2, 3, 51, 1, and 20. And if I do v2 and you sort them with v2, it works. Still don't get why. So and the ordering of v2 is 5, then 3. Oh yeah, so first is 20, and then it's 51. Okay, okay, that makes sense. And I'm guessing that the opposite direction, so grade down, is just reversing order. Yeah, okay, that makes sense. It works on an array of any rank greater than 0. Apparently you can also sort matrices. Oh no, okay, it sorts like the rows, I'm guessing. So the first row 2, then row 1, then row 3. This is a lexicographic ordering. The cells are compared item by item until there is a difference. Characters are compared using their Unicode code points. Yes, that makes sense. Okay. Yeah. Yes. To sort an array of any rank, one can define a function sort up. I don't know what this little guy means. I'm guessing this is just like the indexing operator, but like infix. So sort up. So if I do like, I don't know, 1 of 2, 3, 4. Oh no, okay, so it's 1 of, is this character? 3, 4, no. What's that, that thing? Ah, this. So is it like 1 of 2, 3, 4? Okay, and this is just maybe 2 of 2, 3, 4. This is like the square brackets, but in fix. That makes sense. And this will return the indices. But so if I do like 2, 1, 3. Length error. Okay, there is also this, which I don't understand. But so if I do, does this convert it to a matrix? Okay. I'm assuming this converts it to a matrix, which apparently is needed. To sort an array of any rank, one can define a function. Yep. Yeah, okay. Yep. Grade down. It behaves in the same way, but grade in descending order. Makes sense. As of version 17, you can grade any array as long as it doesn't contain references. The rules for this are complicated and can be found on... Okay. Okay, we can sort arrays of like vectors of characters, which makes sense. Then there is a very complicated example, which I'm guessing we can sort as well. Grading can be used for more than just sorting. To get the index of the maximum value of an array, just use whatever this little symbol is and grade down. To get the maximum value of an array. How? And also this isn't the maximum value of an array. What the fuck happened? So it returns this, and with the little thingy, it returns 5. I don't get it. To get the index of the maximum value of an array, so it's the index of the maximum value. Okay, so I'm guessing the little how can you call it? Like the horseshoe thingy, whatever that is. Just get the first element. So this is like head, I'm guessing. I mean, let's just test that theory. I just do this and like this returns 3. Okay, yeah. So this is a head. And so what if we want to get the maximum value of a thing, we could do like v2, which is still this. and we do v2 and we index it with the first element of sorting them down of v2, which is 51. Yeah, okay. And if we want to get the maximum value, we do the opposite, where we sort in ascending order, and this is 1. Okay, makes sense. Okay. Grading up of something is another useful function, while grading up omega gives you the indices that sort omega. Grading up gives you the position that each element of omega would occupy after sorting. You can also think of grading up as inverting the permutation you give it. So I'm a bit confused, but let's just try it. This would give it this. Doesn't really make sense to me, but okay. As inverting the permutation you give it. So, okay. Yeah, I cannot really find a pattern in that. The first element 4 is the third smallest element. The second element 6 is the fifth smallest, and so on. Oh, okay. And like 8 is the sixth, sixth smallest, and 1 is the smallest, and so on and so on. Okay. Okay. It's fairly common to use double grade up to normalize a vector v to a permutation of a little squiggly thing, triple equal different v, which has the same ordering as v. Okay, let's see what little squiggly thing. I know I thought it was like to generate 10 numbers. It is. And if you use it with a vector, it does stuff. So yeah, I'm not sure what this does, but okay. And it does this. And what does this do? Like the triple equal difference? This looks like it's just the length. But then you combine it with this. Okay. So this is just to normalize vector to a permutation of this, which has the same ordering as v. Okay, they're getting too weird. Like, okay, I mean, I understand that it's the same thing, but that it's a permutation of whatever this is, but I don't understand why they mentioned that. Dyadic grade can also be used dyadically for character arrays. Alpha grade up omega will grade omega according to the alphabet alpha. So if I have an alphabet and I grade hello world, yeah, that's okay. So yeah, instead of like the lexicographic ordering, they use like a custom ordering. That makes sense. So I mean they use like a very strange complex examples, but if I just say like if I just want to say that 2 is first and then there is those ones, then we do grade up of what, like 1, 2, 3 domain error. What do you mean domain error? What do you mean domain error? Do I need to like put stuff in parentheses? Nope. Nope. Well, I guess I don't get it then. Okay, so it works with that, but not the other one? Hmm. Yeah, okay, whatever. I mean, it works with letters, I guess, but not numbers for some reason. Where we sorted the vowels before the consonant, if characters are missing from the alphabet, they will be considered after the alphabet and equivalent. Okay, sure, that's all fine and dandy. And that's it. Okay, so you can grade up and grade down, and by indexing with the grades, you can sort an array. And then there is a weird shit where they do like double grades, but whatever. Okay, modifying rank and depth. Poum, poum, poum. This notebook covers the monadic definition of up arrow, down arrow, whatever this is and whatever this is. The horse iron thing, whose return values tend to differ in rank or depth from their arguments. Mix monadic upward arrow mix is a useful function for creating higher rank arrays. Mix assembles the items of an array into a higher rank array with one of less level of nesting. For example, given a vector of vectors, it returns a matrix with each vector as a row. It's useful for creating higher rank arrays. So they have like 3 vectors, and then they just put them in the ranks. But what if I thought like this would automatically do this? Okay, so I'm guessing this is like an array of array, and this is a matrix. Okay, it's to convert between arrays of arrays and matrices. At least that's my first guess. And then I'm confused. Like, what's the difference between arrow and not arrow? Okay, so they changed the shape by putting it 2 by 2 instead of like. It was already 2 by 2, but like different. Okay, I'm still not clear on the whole rank versus dimension thing. If the vectors in the arguments are different in shape, a fill element is used to pad the array to a rectangle. The fill element is the type of the first element. Typically, the number 0 is the typical, and the typical character is space. The type of an array is the array the types of its elements. That doesn't sound English, but The same array, but where each simple scalar is replaced by its type. Okay, so it defaults to 0 or spaces. The field element for 7, 8, 9 is a type of 7, 8, 0, 0. Okay. When mixing a vector of higher rank arrays, the result will have the A rank one more than the array of the greatest rank in the argument. Fuck's sake. Okay, this is so confusing. Please give me a practical example. I mean, I understand that they convert, they give it a higher rank, but I'm not sure what a rank is, so it's kind of useless for my understanding. Yeah, again, so if you take that without the arrow, it will put them kind of in one dimension, but here it puts them in a higher rank, which makes it 3-dimension, I guess. Okay, can we move to like not this? Okay, split. So I'm guessing split is the same thing but down. Monadic split is the counterpart of mix. It converts a higher rank into a nested array. Converts a higher rank array into a nested array. The result of split will have yeah, okay, it's kind of what I said now, where this thing is an array of pointer to matrices, but if you apply the mix operator to it, so the upward arrow, it converts it into a matrix of matrices. And I think this just maybe changes it in memory, or like this is an array of references. This is an array of arrays of arrays an array of array, and this is an array of references to array. Maybe, not sure. So yeah, but split does the opposite. So yeah, I mean that makes sense. The shape of an array split. So give me an example, quick. So a 2x2. So this is like a 2x2 matrix, but then you mix it down and it becomes an array of pointer to arrays. Okay, I think. And so yeah, they just use the same example. And I guess if you apply them one after the other, they just cancel each other. Yeah. If the argument is a vector of v, its rank is 1, splitting it, the result is an array of shape null whose content have the shape of v, a scalar that itself contains a vector. Okay. Numbers and characters are known as simple scalars because of their depth 0. Splitting a simple scalar does nothing. The result is the argument itself. However, splitting nested scalars increases their absolute depth by 1. Okay. Okay. Mix also will do nothing to a simple scalar, but will increase the depth of nested scalars by 1. So if I have like 1, 2, 3, so I have just this, and then I do the little upward arrow, which is there. It doesn't do shit. I thought it did. Is it the downward arrow then? Because, okay, it splits it. And then if I just put more arrows, oh, so only maximum rank is 5. So it increases the depth. Okay, and so here I have 1, 2, 3, 4. And if I cancel one of them, I should have only 3. 1, 2, 3. Okay, that makes sense. I mean, makes sense. Kinda. It makes sense that they both cancel out each other. A common use of mix and split is to perform matrix operations on a vector of vectors. For example, transpose. Nice. Yeah, I don't know about nice. My brain is burning right now, but but yeah, so they have like an array of arrays. So okay, there is an array of array characters, but then if we try this, I'm guessing this like the whatever O with the bar in it on this, I guess there will be an error because it has to apply on matrices and not arrays of arrays. Or it just does nothing apparently. But if you convert this, to this array of array to a matrix using the arrow operator. Now it's a matrix. And now you do this with this and then this. So this is a transpose operator apparently. And you get the transpose of this, which makes sense. And then what they do is split it back into an array of arrays. So take this, so which will return me the matrix, but then you split it, so you put it back as an array, and then it gives you back the array of array. Okay. Enclose, monadic. This enclose is used simply to enclose any array to form a scalar. It will increase the depth of an array by 1 unless applied to simple scalar where it has no effect. To enclose any array to form a scalar. Okay. Not sure I get it. So, what if I put 2? Isn't this the exact same thing as the upward arrow? Or does it work on scalar as well? No, it does not. This is useful in conjunction with scalar functions or any functions that treat scalar differently. Okay. Okay. Then, how does that work? So it's like this vector plus 1, then this vector plus 2, then this vector plus 3. Yeah, I guess that makes sense. So if you increase the depth, it will simply to enclose any array to form a scalar. I don't know the to form a scalar part, but I understand that it increases the depth by 1. Okay. Here, 1, 2, 3 is added to each of 4, 5, 6 separately. And so here we have just a 2x2 matrix. And then if we enclose the two, oh, this is funky. Okay. So before oh fuck, no. So this expression is like this. So it's just a 2x3 matrix, and they reshape it to 2x2. So they do this, and then it's just this matrices, but reshaped to 2x2. Okay, I cannot write it, but it's basically this. So then you reshape it to 2x2, like so. But if you apply the little the enclose operator, so you have this, which is a 2x2 matrix, but then you have an array of this 2x3 matrix, sorry. And if you apply the reshape operator, it's gonna reshape, it's not gonna reshape this, it's gonna reshape the entire array. And since it repeats itself, it will create 4 times the array instead of how do I do the little row thing? Okay, yeah, that makes sense. Okay. Simple scalars cannot be enclosed. Yeah, I mean they can, but it's just useless. Disclose, monadic disclose, also called first, is a counterpart of enclose. It will take the first item at depth 1 from an array. For a nested array, this has the effect of undoing the enclosing. Okay, it's just the opposite operation. This is trickier. So you... Okay, it's the same example as before, but you disclose it. So if I take this, which was the example we had before, and we add a disclose operator in front, it will just remove the arrays and concatenate all of those in a single matrix, I assume. No, it won't. Fuck. Then how does this work? So they enclose it here, then they reshape it to 3x3. So what is this? Then they enclose it in an array. Okay, that makes sense. And then then they reshape it to 3x3 somehow. They disclose it. Okay, that's a bit unclear. That is a bit unclear. Wonder why this didn't work. Pum, 3x3. Yeah, okay. Modifying rank and depth. Okay. Random numbers. Yeah, that should be easier, I hope. That should be easier. The question mark implements the roll function in APL. Roll n will return a number pseudo-randomly selected from integers in whatever this squiggly line means, with each integer having an equal chance of being selected. Okay, so it's like this will generate an integer between 1 and 10 if it can execute it. Okay, that makes sense. That makes sense. List the first 6 integers. Yeah, okay, yeah, that makes sense. Now generate one of them at random. Question mark 6. Okay, that makes sense. Try it again. It has a 1/6 chance of being the same. Yes, yes, yes. If you kept executing question mark 6, it would be like rolling a 6-sided die over and over. But what if we have 5 dice? Oh! APL functions can take arrays as arguments and return arrays as result. There is another way of rolling 5 dice. Here is another way of rolling 5 dice at once. That okay, so it's like 6, but you reshape it as a matrix of, I guess, just 5 of dimension 5, which is just like making an array. Okay, so this is just a vector filled with 6s. Yes, okay. And now let's look at some ideas about probability. The casino table game known as craps uses 2 six-sided die that are added to give results in the range 2 to 12. The table of all possible rolls looks like this. Yes. Oh, we can apply an array to this little squiggly range function. Okay. And the totals are given by summing each roll, in this case using APL's each operator. Okay, so each operator is 2 dots. So we have the matrices of all possible dice roll. Then we have the each operator, and we have this is like reduce sum, so it's like just doing the sum of each of those. So for each cell of these, we're gonna do the sum. So it should be 2, 3, 4, 5, 6. Okay, okay, okay. And the last one, 12. All right, yeah, that makes sense. Yes. So first, let's create a function to compute the elements of the range results. Compute the elements of the range of results. So -1 row, comma w, but comma means something else. God damn, there is no way I'm understanding this. Range is 6, 6. Yes, maybe, maybe not. What the fuck is going on? Okay, so they have this graph thingy, which I'm not gonna even attempt to read, but it creates a graph. Fuck's sake. It's nice that you can actually do somewhat visual representations of stuff as well. But so does it say like the probability of having each score? So you have like or like the count. I don't think it uses random though. Huh? No, okay. Thing is just like the probability distribution, kinda, of like the score you could get with two six-sided dice. Okay. But yeah, they jumped from, oh, we're doing like little question marks on multiple elements to, what the fuck? uh, uh, don't even understand. There is no question mark in this. Whatever. I can use question mark. Let's go. Boolean function and Boolean algebra. What is there? Comparison functions. That should be easy enough. 6 APL functions, so that's pretty intuitive. Like minus than, minus or equal, and so on. Less than or equal. We use this function to compare the arguments. Dyadic, scalar function being dyadic. Left and right. Okay, you need 2 arguments. Makes sense. Not equal to, less than, greater than. We start by exploring a bit of this 6 scaling. Okay, let me clear this. A forward on logical values in APL. Depending on what your program background is, if any, this may come as a surprise to you, but in APL, the logical values, the things we use to indicate if an expression is true or false, are represented with numbers 1 and 0. No, that's perfectly fine. Yes. Okay. Equal to. Yes, that makes sense. They understand that they can cast the stuff, that's cool. Yeah, they work with letters, awesome. Works with complex number, aggregates. They can do it on vectors, that's nice as well. For comparison scalar is that we can have a simple scalar on one of the side. Okay, they can like apply this operation to multiple elements of vector, like map it. Yeah, okay, that makes sense. All of that is pretty intuitive. I'm guessing that also works with nested arrays. Yeah. Okay, but this breaks down as the two. Okay, not equal to. And this is, I'm assuming exactly the same to the other one, comparing things other than numbers. Yes. Oh, domain error, okay. Greater than, same thing again. Interchangeability of less than and greater than. Okay. Okay. Yeah, that's fine. What is the little squiggly thing? Like so? Oh, this generates 10 arrays. Okay. Okay. Yeah, they haven't explained what the fuck that is. A little smiley face. Okay, but they do stuff. Again, it's very similar. Yeah, yes. Okay, well, that wasn't very interesting. I'm guessing Boolean algebra shouldn't be too fun as well. So maybe let's do not conways geom of light. That sounds hard. Reduce and scan, but okay, so this is absolutely not complete. Like, can I click on something and I get the help? Like this guy. Oh, they do give explanations. They say grade down, this is a monadic function. So if you have the surprised face, dyadic operator over. Same as monadically. Okay, And so, for example, the little this tidal diaeresis. There is no way I'm pronouncing this. Monadic operator commute switch. Okay. Is it just like flipping the argument of something? Looks like it. It looks like it. Okay. Okay. Alright. Maybe I do one last one about reduce and scan, and then call it a day. Poop, let's remove all this garbage. An operator takes one or two operands, which are usually functions, as arguments and derives functions which itself can either be monadic or dyadic. A very fancy way of saying you can pass a function to a function. Slash or reduce is a monadic operator which derives an ambivalent function, ambivalent meaning that it can be used both monadically and dyadically. It is called reduce because it always reduces the rank of its argument by 1. Reduction on a vector is straightforward. So, for example, if I do plus a reduce of 1 to... okay, I cannot type on my keyboard, but 1, 2, 3. And if you execute it, it makes 6. And can I do like 1 plus and then reduce it on 1, 2, 3? That doesn't work. Okay, but so it gives me the sum. Can you give me the like times? That gives me 6 as well, so gives me 18. Makes sense. Reduction on a vector is straightforward, is the equivalent of applying the function to everything. Applying the function diatically to everything, okay, and then enclosing it. The result of a reduction will have the shape of the argument excluding the last axis. The result of a reduction will have the shape of the argument excluding the last axis. Okay. Yeah, that's the example I just did. The result is enclosed because the rank must be 0. Okay, that makes sense. Since the functions in APL are right associative, this has an effect on reduce. For example, minus reduce is alternating sum. So it's 1 minus 2. So this is minus 1, then minus 3. Wait. Would it be like 1 minus... That's quite strange. So it is the same thing, but this is weird. I'm guessing it like reverses sign every time, so it's like minus 1, then it becomes 2, then it becomes minus 2. Alternating sum. Right associative. so they first execute this, which is a -1. For higher rank, arrays will reduce along the last axis. So the columns in this case. Not the columns actually, the rows. Yeah, okay, this is the first axis, tree, and the last axis is the column. Or not, I'm confused. But yeah, this is, it does it row by row. Okay. The twins of slash but with a bar reduces along the first axis, i.e. the columns of the matrix. Oh, okay. Okay. Yeah, that makes sense. If you need to reduce across some other axis, like the second in a rank tree array, you can use f-axis dot. So okay, with the dot you can specify which axis you want to reduce on. That's quite nice. What the fuck? You see, that don't do this. I'm confused, but okay, it reduces on the second axis. And here it reduces on the first axis, and here it reduces on the last axis. Okay, and like reducing on the first axis with the index 1 is the same as the special symbol for the first axis. As a dyadic function, is window the reduction, so the f reduction is sliding window of size L and R to some A. Yeah, that makes sense. That's cool. You can do a window the reduce that easily. Okay. Yeah, okay. Makes sense. Windowed reduction does not change the rank. So yeah, it went 2 by 2 here, it went 3 by 3 here, and still did the sum of all of them. Okay. If the left argument is negative, the windows are reversed. What do you mean reversed? -2. Common use of reduce are for sum, product, and with and or. Alright. Well, my brain is filled with new concepts, and I'm gonna go eat to digest all this shit. Oh, mon dieu. And I think, yeah, this website is nice to be like quick interactive stuff, but maybe I should watch more in-depth tutorials about all of those symbols, because I think there is like a lot of them that they use in the example, but they don't really explain the meaning sometime. But a Sudoku solver. Okay, I'm just curious. I'm just gonna run through this really quickly. So you can do backtracking. That's kind of nice. Okay. Let me just see. So they generate a Sudoku grid. And next is like the next position in the backtracking. And they can do a tree search just with arrays. It's kind of insane. Okay, but show me the end result. Quick, 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 come on. I believe in you. This is gonna take a while. So I'm guessing they generate it randomly and then they use the solver to solve it. But that's yeah, it's very impressive. It seems like a headache to write. Maybe not once you get used to it. All right. That's pretty cool. That's pretty cool. Oh, you can have also the N queens thing. Damn, that brings me back to school. Anyhow, see you later. My brain no working anymore.